Okay, so before I start, just to make sure that uh, you know what I'm planning next week. So next week, uh, maybe Wednesday or Thursday, we are going to have a makeup exam. So makeup exam, chapter 10 and 11. Okay. Will be only 1 hour. So questions will be 3 to 4 questions only. This will be optional. Okay. So makeup exam, optional. So you can choose whether you want to have the exam or not. Okay. And my plan for the score will be 40% plus 60%. This is the old score and then the new score. So for example, if you get maybe like 40, so you need to multiply with 40% plus, and you get maybe 70, then this will be your new score. Okay. So at least it's getting a little bit higher. If you get 40 on your old score and your new score maybe 38, it's lower, then I will just take the 40. Okay? I will take the higher one. Okay? So it's actually, you can just try and try and then see the score. If it's lower, then I will just take the higher score. Okay. But I think I will open a chance for you to get more score. Okay. And topics like chapter 10, the area, either parametric or polar, or I still feel 3 or 4, so it can be arc length. And chapter 11, mostly about series. It can be converged, diverged type question, and also the Maclaurin or Maclaurin or power series. Okay, I think that's it. And I will announce later in the Moodle to let you know. So the next part is we are going to continue the sections on the maximum and minimum value. As you may also know from calculus 1, this is actually similar problem, but now we are looking at the 3-dimension space. So we have the same, finding the absolute maximum, absolute minimum, local maximum, local minimum. Okay. And if you see from this picture, I think you can guess what is the absolute max, absolute min, local max, local min. What do they represent in the graphs, right? So if you say local, it means that it is locally nearby that point. For example, if I say the local maximum, so nearby this one here, if you can see, nearby this point, the point on the top, this one, we say it's local maximum because beside this point, we see that the other point is they are lower than the local max. Right? So we are looking at locally. Similarly with the local minimum, we see this point is become the local minimum because nearby that point, other are higher than this point, where the absolute maximum and absolute minimum is basically from the whole graph, from the total graphs for the total points, the absolute maximum is the highest one. The absolute minimum is the lowest one. Okay. So by definition, if we want to write in a word so that we can also write in the inequality, so a function of two variables, they are having local maximum at some point a, b, if the function nearby the point a, b is less than the f of a, b, the a, b value. So the key point for the local maximum is nearby, near the a, b. And we call the minimum if the function is greater or equal than the f(ab). Okay. And again, the key is nearby. Okay. So we say that we can have a local maximum and local minimum. Okay. I think very clear. For the local max and local min. Okay. Okay, and then remember in calculus 1, we have function of x, right? And then we are having the first derivative, right? And then we have the second derivative of x, right? And this represent, okay, the first derivative represent increase or decrease, right? Or decrease function. And the second derivative represent concavity. Okay, what's concavity? Concavity is when you have the graph like this or like this. It's going upward, downward. Increase, decrease, like going up, going down. Okay, and then you know, like you will have a maximum here or minimum there. Okay, this is concave upwards, concave downward. Okay? So similarly, in calculus 2, when we have function of two variables, then we have what we call the critical point. Okay? The critical point is when the f prime we call critical point when it is equal to 0. So this x is critical point. So in calculus 2 now, in our partial derivative, so if f has local max or mean at certain point AB, and the first order partial derivative of f exists, then we say partial x at AB will be equal to 0 and partial y of AB also 0. This AB then we call the critical point. Okay. The point AB is called a critical point. Okay, remember that in calculus 1, I would like to make some emphasis. Okay. We may have graph just like a random graph like this, right? And we certainly know that here, here is max, right? This is min, okay? If I change this graph, for example, like we have something like that, okay? So it's going up, and then it's stationary, and then it's going up again. We know that when we're going up, this will be the f prime x is positive, this also the same, also positive. Okay, so positive and then positive. So according to the definition of the max or min, we cannot see any max or min here, right? Because it's going up and going up. Okay? The local max and local min is we cannot see, right? But if we try to use this critical point definition from the calculus 1, this line here, the slope is 0, right? The slope is 0. So it's also critical point. So it's a critical point, but it doesn't necessarily to be max or min. Okay, this critical point is not max, not min. Okay, the same thing we're going to see in calculus 2, where this critical point maybe it doesn't mean it will be max or min. maybe something else, okay? Something like that, but in three-dimensions. Okay, so let me give you some example. Okay. Okay, let me give you some example. So let's say we have a function of y squared minus x squared. So since we can easily partially derive, so partial x is negative 2x and partial y is 2y. So the only way we could find the critical points, we take this equal to 0, right? Which means that x is 0 and y also 0. So the point, so the 0, 0 is the only critical point Okay, so if we put the point 0, 0 in the function, so f 0, 0, okay. So for example, if we put the x equals 0, so if we put, let me write one by one. So if x is 0, so 0 y, okay, this become y squared, right? And if we have y equals 0, this will be negative x squared, okay? So this will be a positive function. This will be negative because of the negative signs. It's less than 0. So every area within the surface nearby the 0, 0. Oh, wait. Okay, so nearby the 0, 0, there will be, so near 0, 0, the area contain points where f is positive and f is negative, which means it's not maximum or minimum, so it's something else. If you remember, this y squared minus x squared, we call this the elliptic or hyperbolic parabolic. So hyperbolic, this hyperbolic and what's interesting about this hyperbolic paraboloid is only 0, 0, which is on the middle here. So if you see from this picture, I hope it's clear. It has like that, like a saddle when you ride a horse. So this point, it's not maximum, it's not minimum. You will see that because there are some other that nearby the area is downside and some other is positive. See, it's positive from the y, this is y, right? And then when it's in x-axis, it's negative. So you see the y squared and then the x squared according to the z. Okay? So this point we call with another term which we call the saddle point. Okay, pretty obvious, right? It's like a saddle, so it's called a saddle point. So this is not max or min. Okay. So finding the critical point, not necessarily to be maximum or minimum. It can be the saddle point. There is one method to check whether we are having a maximum, minimum, or saddle point. Okay. We are going to implement the second derivative. Okay. So we have the first partial and we have the second order partial. I don't know why this always happens. The cable is so sensitive. Okay, let's check the method. Okay, how to test the second derivative. This is the method. The second derivative test. So suppose that we can partially derive, okay, and then we already have the critical point, the partial x equals 0, partial y equals 0. So we have critical point at the AB. Okay, so AB is critical point of f. Sometimes, okay, to find the critical point, we need to solve partial x and partial y. Okay, so we need to solve and then maybe substitute x and y and make some conclusion until we get point. Okay, until we get the point. So we make it equal 0, make it equal 0, and then solve and finding the point. Okay, and then we are going to use what we call D as in it's actually the determinant from matrix. So the partial XX multiplied with partial YY, which means the second order, the second derivative, we partially with X and then with another X and this Y and another Y minus the partial XY or YX, they are the same, right? And then squared. Or let me write, maybe to make it easy, we can write D as the determinant of this actually from here. Okay, so this will be f. Okay, so that's D. So this D will determine how the point in the graph will be behave. For example, if D is positive, okay, and then the second derivative of xx also positive, then the point will be local minimum. If D is positive, but the partial x-axis is negative, then the point will be maximum. Okay. But if D is negative, then we can confirm it will be saddle point. Okay. So D is either positive or negative. When you get negative, then it will be saddle point. If it is positive, check the second partial x-axis. The partial x-axis. If it is positive, then the minimum. So positive, positive minimum, positive, negative maximum. If negative D, then it's saddle point. Okay. So our goal in this chapter is usually finding the maximum, finding the minimum, and also finding which one is the saddle point, which point. Okay, so let me give you an example. So let's say we have a function okay, we have that function is for there are some proof for the second derivative test, but I think you don't need to prove. Maybe later if you have time I will give you. It's basically the proof is from the directional derivative. But I think too long. Maybe just skip that one. Okay, so we need to find whether we have local max, local mean, or saddle points. So first is taking partial for x. So 4x minus 4x cubed 4y, right? And partial y is 4y cubed minus 4x. So we can write this in terms of 4x cubed minus y is also the same. Y cubed minus x. And then to find critical point, so find the critical point. So this is the first step every time. So every time you need to check the local max, local mean, the saddle point. First finding the critical point. Okay. So find a critical point. So x cubed minus y equals 0. Okay. 4 becomes meaningless, so I just remove 4. And the other one will be y cubed minus x equals 0. This is what I mean by we need to solve this first. Okay. We need to solve. So either you substitute y, we go here, and y will be equal to here, or from here goes to here, same thing. Okay. So that we need to solve first. So let's solve that. So let's say we are going to substitute the y equal x cubed. So this x cubed and then power again with 3 with cube equals 0. Okay, so substitute to here. Let me move a little bit to the right left. Okay, now we get x with power of 9 minus x equals 0. We can factor x out, so this will be x with power 8 minus 1. Now what can we do? The x with power of 8 we can factor, right? We can factor become x power of 4, right? This will be x4 minus 1 and x4 plus 1, right? And again, the negative we can factor again, right? So this is interesting. So let me write the plus first and then the second one, or maybe let me change this. This become plus, this is minus. So this is x squared plus 1, x squared minus 1. So we can still factorize, I think. So x plus 1, x minus 1. So we can see that there are at least 3 possibilities from this, and this, right? Because the other two will be, I think will be similar, right? So we have x. So the solution for this is x. So this equals 0. Forget to write 0. So x equals 0. X equal negative 1. X equal 1. So we have 3 x's. So when x 0, y is 0. When x negative 1, y negative 1. When x is 1, y is 1. So we have 3 points, right? We have 3 points. So critical points, you can write here, critical points 0, 0, negative 1, negative 1, and 1, 1. Okay. So this 3 is the point that we are going to test on the second derivative test. So next part, we are going to find fxx and fyy and also fxy or yx. Okay. And then we put into the equation, and after we get from 0, 0, negative 1, negative 1, 1, 1, we finally get which one is max, min, and the seventh one. Okay. So let's check the second partial. I think I will copy this part. Let's copy. And let me write a new page here. So this will be okay. And I think we can erase this one. Okay. Or maybe let me make a space here. Okay, so or maybe let me erase this one first. So finding the fxx, so this will be 12x squared. Fyy, this is 12y squared. Okay. And fxy is negative 4. So it's already a number and it's negative. Okay, so we put all the tests. We can write the d as fxx fyy minus fxy squared. So this will be 144 x squared y squared minus 16. And then we can put into the equations. So x, y, this is 0, 0, negative 1, negative 1, 1, 1. This is d, and this is partial x, x. Okay. So we put 0, 0. So it will be 0, so we will be negative, right? So D is less than 0, for sure, right? It's negative. So 0, 0 is saddle point. D is here, this one. And then we put negative 1, negative 1. Since it's having squared, so it will be positive. So we have a positive. So we need to check the fxx, which also positive, right? So negative 1, negative 1, already right here, fxx is positive. So the negative 1 is local minimum. This is also the same, and this should be the same as well because of the squared, so it should be the same, positive. So 1, 1 is local minimum. Okay. Now if we would like to draw, let me, I put here, let me just cut and copy this. So this is the picture. And then copy again. So as you can see, our 0, 0 is this one. And we have two local minimum, which is the negative 1, and 1, 1. If we look from the top, this will be the level curve. So we have a counter, which is, this is going to be the one that is the minimum, this point here. And the middle is the saddle point. Okay. Okay. Like actually, like this counter level, like if you think like in the future you want to maybe study more on geophysics or geophysics engineering, like mapping the land, the counter, you will like maybe mostly dealing with some method to simulate the how the surface looks like. I think now people using drone. So now the technology for the drone, as far as I can remember, if the drone is super capable, like usually they have like the radius when they scan through the camera. Sometimes I think the most advanced one, they can map the area and then make this kind of contour directly. So you can map like which one is the mountain, which one is the building. I think some of the drones can have that. Like now they have the technology. So if you are maybe want to explore that, I think it's also good. Now, I think it's good for exploration, especially for finding where is the resources. Like for oil, gas, you need to do some mapping first, and then you can predict, because there is some method to, or some formula to find where is the most resource area, the highest resource from that method. Okay. And you will see like more or less like counter like this, but I think more complex, because it's basically the surveys of maybe mountains like area. Okay. Okay, the next one is some applications of the max minimum value, which sometimes is related to how we can find optimization. Okay, like in calculus 1 we have optimization. We find how to, like, we have some formula, like relations to the as a function, and then we can maximize or minimize those formula. For example, how to find the maximum profit, blah blah blah, or maybe maximum like geometry, maximum volume, area, and so on and so forth. The same thing with our partial derivative application. We can also find, for example, find the shortest distance from some point, and then we need to find to the plane which is somewhere along the three-dimensional space. So we have a point, and then we need to find the distance to the plane. If you're maybe not familiar with this, let me just give you the idea. So basically, distance, let me make it bigger. So distance, like for example, this is the point. I'm just drawing a little bit random. So this is going to be the distance, or maybe to make it more realistic, this is the distance. And then we have the plane maybe here. And maybe that's the plane. Okay, so basically the distance for this is, we are going to take so let me write here, distance from any point to point 1, 0, -2. So we write the definition first for the distance, which is this will be x minus 1 squared plus y squared plus z plus 2 squared. Okay, so because this point, because it's from any point, and we have the plane, right? We have the plane which is x plus 2y plus z equal 4, which means that this is, we can substitute, right? So we can write z as 4 minus x minus 2y. So we can substitute the z inside here. Okay. So we define that z is the same here. Right? Z is the same at the point that we are going to evaluate our distance. Okay. So we can exchange z inside. So d will be, still writing x minus 1 squared plus y squared, and then plus 4 minus x minus 2y put inside, and then we plus 2, so it becomes 6, right? So it becomes 6 minus x minus 2y squared. Okay, so if this is our function, for our function of two variables x, y, the square root may be too complicated, right? So, because this is modulus, right? This is modulus. And what we want is we want to find the shortest distance. So to make it minimize, we can just make a model that is just maybe taking the d squared. Maybe that will be a better model. Okay? So we can take the model as d squared. So we can have this, which is much more simple when we take the derivative, right? If we are going to take derivative, the first one here, we are dealing with the square root. But if we take squared, it will be a better model. So let this become our function instead of this one. Okay. So let this become function. So let function is d squared equal, or maybe just write directly and write the whole thing. Okay. So now we can simply partially derive with respect to x and y. Okay. So we can find the critical point. So the same thing, we find the critical point first. Do you mind if I continue and we can early finish? Okay. I think that's better, right? It's Friday, right? If you don't have any class later, it would be good to finish earlier, right? Okay, so we can take this as partially derived with respect to x. So we derive 2 and then x minus 1. I think that's the first one. And then the second one is on the right side. We have negative 2 because from the negative x. Right again. Okay. So it's actually coming from 2, 6x, and then multiply with negative 1. So it becomes negative, okay? And the same thing with partial y. We get 2y, and then we have negative 4, right? Negative 4 because 2 going down and then multiply with negative 2, so negative 4. And then 6, that's x minus 2y. I think we can solve this just to make sure it's correct. So 2x plus 2x is 4x. So plus 4y. And then minus 12. Minus 12 minus 2 is minus 14. This one, 4x plus 2 or plus 8 plus 2, so 10, and then negative 24. Both of these need to be equal to 0. I think we can solve by linear equation. Okay, so we can subtract this. So 4 minus 10 is negative 6y. 24 minus 14. It's 10, right? Or no, 10. Let me check the number. 4x plus 10y, okay. So it's 10, right? So y is negative 10 over 6. Or what? 5 over 3. Oh, wait. Should be, I did something wrong here. Should be plus 10 equals 0. So y is 5 over 3. Okay, now we can substitute back y to the system to find x. I think it's a fractions, not really a good number. So we substitute back x, so 4x plus 20 over 3, right? Negative 14 equals 0. So 4x is so 3 is 42. So 22 over 3, right? 22 over 3. Yeah, 22 over 3. And then x is divided by 4, so 22 over 12. Divided by this 11 over 6. Okay, so we get the critical point is 11 over 6 and 5 over 3. And then we check through the second derivative test. Let me write the second derivative on the right side. So check, so fxx is 4, y is 10, fxy is 4, right? So d is fxx fyy minus fxy squared. So d is, we can just calculate 40 minus 16, or d is 24, so it's positive d. So d is, so since d is 24 and the partial xx is 4, so both are positive, then at will be minimal. Okay, will be minimal, but it doesn't answer the question. The question is asked the value, so we can just input the value. So we need to input, so input the 11 over 6, 5 over 3 to d. So d, but when we input, so this one, we use the model to find the minimum point. But when we get the point, we need to put to the equation for the distance and then finding the value. So this will be x minus 1 squared so x minus 1, let me write x minus 1 is 11 over 6 minus 1. It will be 5 over 6 squared plus 5 over 3 squared plus 6 minus 11 over 6. So 36 minus 11 is 25. 25 over 6 minus 25 over 6. 25 over 6. So 2y, 10 over 20 over 6. So 25 minus 20 is 5. So same 5 over 6 squared. So you have 25, or you have 50 over 6 plus 25 over 3. So 50 plus 50 is 100 over 6. 100 over 36, 100 over 36. Or in our case, this will be 5 over 6 square root of 6. So this is the shortest distance. So the shortest distance, is this. Okay. Maybe one more example and then one more section and we can finish. Okay. So let's see. Oh, I didn't prepare any questions. So let me write the questions. So a rectangular box without top or lid is to be made from 12 meters squared of cardboard. Find the maximum volume of box. So you have a box but without top. Or maybe let me design with this. So without top, so no top. The volume itself, if we take z, this is y, x. The volume itself is x, y, z. Okay. And then the other information that is important is this 12 meters squared. So which means that we have some cardboard and we want to cut. But how much our design is based on this volume x, y, z. So what's the length of x, y, and z? That's the question on this. So we have x, y, z as our volume, and we have this 12 meters squared of our cardboard. So we can think this 12 meters squared as the area. Okay? The area of this plus this plus this plus this plus this without the top. So we can add all this and equaling that area with the 12 meters squared. Okay? So we can take 2yz plus 2xz, okay, plus only xy, okay, because without the top. This should be equal to 12, right? Now, to minimize or maximize, we have three variables here, x, y, z. But our z, or our x or our y, we can substitute from here. Okay, so we can solve maybe for z and then substitute to this z here. Okay. So we can solve this z. So we can take this z is 2y minus 2x, and then let's say this is 12 minus xy, and z is 12 minus xy over 2y minus 2x. I think that is already in terms of xy, so we can substitute to our volume. So this can be put inside the volume here, okay? So the volume is xy and multiply with 12 minus xy over 2x, wait. Oh, this should be plus, sorry. 2x plus y. I think just multiply these two, so 12xy minus x squared y squared over 2x plus y. Now to compute the derivative, we need to have the quotient rule. Okay, now we can compute v partial with x. So this will be 2x plus y squared, okay. And on the top will be quotient rule. So f prime, so 12y minus 2xy minus, or maybe let me write this as in, let's square all of that, and then this will be 2 multiply with the whole thing here. Oh, I forgot to multiply. And move this a little bit to there. So 12xy multiply with 2x plus y. Okay, sorry. It's a little bit long. Can we make something from here to x? If we multiply, it's to be too long, I think. So let me write here 2x plus 2y. Oh, should be okay, no. This should be x y squared. So let me check first. Negative 2x. Okay. Xy, x squared, y squared. Okay. I think we can make this. So we can factorize x, and this will be 12y minus xy squared. Okay, that's good. So we can factorize this and this. So write 12y minus 2x y squared multiply with 2x plus 2y minus 2x. Okay. This will be 2 x plus y squared. This will be cancelled. And this will be what? 12y or 2y in the front, 12y minus 2xy squared. Mm-hmm. 2x, 2y, okay, 2x, 2 plus this and that, okay. And this will be 4x plus y squared. It can be cancelled, this become 2. And we can factorize, become y squared, 12 minus 2xy. Okay. Oh, I think. Oh, I make a mistake. Really sorry. It should be a product rule. Okay. minus 2x squared. This is good. 2x plus y. Is there any mistake that I make? Maybe just write this first. Okay, maybe just write this as it is first. Okay. I'm not sure the answer. Maybe you can check later, okay? The answer should have, I will check later, should be like this, 12 minus 2xy minus x squared. I also haven't checked the computations. It should be this. Did I somehow missing something here? I think no, right? Anyway, let's do you think, do you know the mistake?
Y minus xy is good.
Oh, here?
Yeah.
Yeah, I put x here.
In the front is 12y minus 2xy squared.
Oh, this one.
No, I mean the same equation.
Same equation, go y. Yeah,
In the front.
here, right?
No.
I can compare. Which one? This one, right? So y.
This is 2xy squared. This is xy squared. So.
No, I mean this one is from the differentiate this and then multiply with this. So this actually comes from here. So this is the top. Okay, this is the top. Multiply with the derivative of this, right?
Yeah.
So and I move the x outside here becomes of y, and then this x.
So how does this come from?
Oh, wait.
You put this here and use this way.
Yeah, 12x plus 2y minus.
But this is not the same. You can just is that right?
Oh yeah. Ah, okay, got it. So then, what should I do now? Anyway, maybe you can help me later, okay? After we finish, or maybe if you have time later. But the answer should be this, okay? So I will write some question mark. I will try later again. So this will be wrong, right? This one should be not this. So we need to check again this part. So especially here and here, okay. But the answer for the v, for the partial x, is that, and then for the partial y will be this. I don't think this is wrong, but this is the answer that the final result should be. But later we can check. Okay? Maybe I put some wrong calculation here. But anyway, to find the critical, then all this need to be equal to 0. Right? So the Vx equals 0 and Vy equals to 0. But if we put y or x, if we put equals 0, then v is equal to 0. So we don't want that. Right? So we can think on this one and this one. So we can rewrite that. We can write that solving 12 minus 2xy minus x squared equals 0 and 12 minus 2xy minus y squared equals 0. So if we just take subtract both of these equations, so we are getting that negative x squared plus y squared is equal 0. So x squared is equal y squared, or x is basically equal y. And of course, we don't want a negative one, right? We don't include the negative. It can be negative number, but we are not including that one because it's a geometric shape. So if we substitute this equation with the x equal y, so substitute the equations, then we get 12 minus 2x squared minus x squared equal 0, or 12 minus 3x squared 0, we get x equal 2. And because x equal y, so y also 2. And z is from the xy, right? So z is what? Z is this, right? 12 min xy. So 12 min xy. 2x plus y. So z will be 12 minus 4 is 8. And then, so it will be 8. 4 multiplied by 2 is 8. So it's 1. And we can test the second partial test, but I don't think we need, so we can just write the volume is 2 multiplied by 2 multiplied by 1. It is 4. This is the maximum value that we can have. Or 4 meter cubes. Okay, now one more section and we can finish. So the last thing is we have the absolute maximum and minimum. So basically, the absolute maximum is we are setting the all domain on the three-dimensional space. So if we say the point is the highest one for all x, y in the domain, then we say it's absolute maximum. In the previous sections, we only set in the nearby area, which is giving you the local. But for the absolute is for the whole domain, which means that we are going to see that this domain can be determined by some set of intervals. For example, we set the intervals on this D in the two dimension. So maybe we have interval of x and interval of y. So all the principle the same, all the same with the previous one, but in this absolute and max and min, after we find the critical points of the function, we need to find the extreme values, which means all the point we need to test. So test and then which one is the highest one. We also need to check the boundary. The bounded points. For example, you have interval. You need to check the interval, okay, to get maybe there is absolute maximum on that interval. Okay. So, like for example, okay. So you have this, like in like a cone like that. We know that this is going to be maximum here. So if we set on this interval, we need to check this, okay, all this stuff around the interval. And if we find that they are the minimum, then we can say within this interval, this will be absolute maximum, and maybe this will be the minimum minus one. Okay, maybe it's going to be lower, okay, because this surface can be, we can reshape this shape in any way, right? So the largest will be maximum, the absolute maximum, and the smallest will be the absolute minimum. So basically the same with the previous one, but you need to check the point on the interval, okay? The point in the boundary, This is an example, but I think this can be for next week. Okay, so Wednesday or Thursday, make up exam. You can consider if you want to take. It will be 40% your old score plus new score 60%. If you get lower than the first one, then I will use the highest one. Okay.